Hello to everybody. Today we have to discuss some examples on quotient groups. Recapitulation, normal subgroup, cyclic group and abelian group. Learning objectives to introduce the basic concepts of abstract algebra. Second one, to develop the students' abstract and logical thinking capabilities. Third one, to develop the students' mathematical ability to handle proofs. Session outcomes, linking finite groups with quotient groups. It gives interesting methods to count the order of a group. Prerequisites, definition of abelian group, subgroup, normal subgroup and cyclic group. Examples. First one, if H is a normal subgroup of a finite group G, then prove that order of G by H is equal to order of G into order of H into order of G by H is equal to order of G into order of H. Solution. Order of G by H is equal to number of distinct right or left quotients of HH in GG, as G by Hg by H is the collection of all right or right quotients of HH in GG. This is equal to number of distinct elements in G, number of distinct elements in H, that is equal to number of distinct elements in G, number of distinct elements in H, that is equal to order of G into order of H. This is by Lagrange's theorem. Second example, show that every quotient group of a cyclic group is cyclic, but not conversely. Solution. Let HH be a subgroup of a cyclic group GG. Then HH is also cyclic because every cyclic group is abelian. Therefore, HH is a normal subgroup of GG. Also, it can be easily provided that HA into N is equal to HAN into HA is equal to HAN for every integer NN. Therefore, G by Hg by H is cyclic and its generator is HA into HA. Its converse is not true. For example, if P3 and A3 are the symmetric and alternating groups of the three symbols A, B, CA, B, C, then the quotient group P3 by A3 is cyclic, whereas P3 is not. Third example, show that every quotient group of an abelian group is abelian, but its converse is not true. Solution. Let A, B belongs to GA, B belongs to G be arbitrary. Then HA, HB, HB are any two elements of the quotient group H by Hg by H. Then we have HA, HB is equal to HAB. HBA is equal to HB, HA. That is equal to HAB is equal to H into BA, that is equal to HB into HA by the definition of quotient group. Therefore, G by Hg by H is an abelian. Its converse is not true. For example, if P3 and A3 are the symmetric and alternating groups of the three symbols A, B, CA, B, C, then the quotient group P3 by A3 being of order 2 is abelian, whereas P3 is not. Theorem. If A, B are normal subgroup of GG with only the identity element in common, then every element of AA commutes with every element of BB. Proof. Consider u is equal to a minus 1 into b minus 1 into ab, that is equal to a minus 1 into b minus 1 into a into b is equal to a minus 1. Next, b minus 1 into ab into u is equal to a minus 1 into b minus 1 into ab is equal to a minus 1 into b minus 1 into a. B is equal to a minus 1 into b minus 1 into ab, where a belongs to a, b belongs to b, b belongs to b. Since a comma b are normal, a minus 1 into b belongs to ba minus 1 ba belongs to b, and b minus 1 ab belongs to ab minus 1 into a. Thus u belongs to a intersection b is equal to 1. U into u belongs to a intersection b, that is equal to 1. Hence a comma b commute. Next theorem, if H is normal subgroup of a finite group G, then order of G by H is equal to order of G by order of H. Proof. By the definition, we have order of G by H is equal to number of distinct quotients of H. This is equal to index of H in G, that is equal to order of G by order of H. This is by Lagrange's theorem. This is the session summary. Multiple choice questions. First one. A trivial subgroup consists of, the answer is A, identity element. Minimum subgroup of a group is called, answer is C, a trivial group. Third one. Let K be a group with 8 elements. Let H be a subgroup of K and H less than K. It is known that the size of H is at least 3. Then size of H is, answer is D, 4. Fourth one. Intersection of subgroup is a subgroup. Answer is B. Fifth one. A normal subgroup is, answer is D, an invariant equipped with conjugation by the elements of a original group. So these are the reference books for this session. Thank you.